All right, so in our last video, we went over what an annihilator is for a function, and we sort of described how we would use that to solve the types of DEs that we were dealing with in section 4.4. But we haven't done any actual examples of that, and so that's what this video is going to be. Our first example, we're dealing with a second order DE, y double prime plus 3y prime equals 4x minus 5. Now we start this one the same way that we start, or we were starting them back in the previous section. We start by looking at our auxiliary equation. So our auxiliary equation in this case would be m squared plus 3m equals 0. This is going to have solutions m equals 0 and -3 because of how that would factor, and each of these is going to have a multiplicity of 1, which gives me a complementary solution of c1 plus c2 e to the -3x. Okay, so that's fine. That's how we would normally go about that. Now this time, this is where the method is going to start looking different. I am looking for an annihilator of this function, 4x minus 5. It's a linear polynomial, so I know that an annihilator of this would be d2 or d squared. So I am going to use that annihilator on both sides of this equation. Okay, y double prime plus 3y prime equals, I know it's going to equal 0 because that's what this this operator does to that right-hand side. That's what makes it an annihilator. Now, one way I could proceed is I could kind of distribute the d squared in and say, what's the second derivative of y double prime? What's the second derivative of 3y prime? But I'm actually going to do this in kind of a different way. What I'm going to do is rewrite this differential equation right in the the expression in parentheses here in operator notation, so that it looks like this: d squared plus 3d y equals 0. Now, what's my reasoning for doing that? Well, what I've done, first of all, is by using that differential operator on both sides of this equation and sending this to 0 because it's an annihilator for that function, is I've created a homogeneous linear equation right here, evidenced by the 0 that's right there. So I know that because it's homogeneous, I am going to be looking for an auxiliary equation to solve this guy. It will be a different auxiliary equation than I have up here because we've turned this into a new equation. So what I'm going to do is solve this thing by finding the auxiliary equation for it, and leaving it in operator notation like this indicates what that equation is going to look like. It's going to look like m squared times m squared plus 3m equals 0, right? Factor an m out of that, that's actually going to be m cubed times m plus 3 equals 0, which gives me solutions m equals 0 or -3. Now the -3, that root has a multiplicity 1 because it only shows up, or it only comes from one factor here, but the 0 has a multiplicity of 3. I'm going to say multiplicity 3. So what that tells me is that this DE right here, which is the same as this one up here, but I have it in operator notation right here, this guy is going to have the solution y equals, using my 0 with multiplicity 3 here, it's going to have c1 plus c2x plus c3x squared. Remember, that's case 2 of what it looks like when we solve an auxiliary equation for a DE from like 4.3. That's the case 2 situation from 4.3. Then this -3 right here is going to give me a plus c4 e to the -3x. Now notice something, okay? Because what we're doing is we've manipulated this equation by performing a valid operation on both sides of it. Namely, we applied that differential operator to both sides. And so what that led to is kind of an equivalent equation in a sense, and this is the solution of that equation. Well, this solution is kind of a general form of what we would expect the solution of this equation to be. And if you notice, some of the terms here match what we're seeing in our complementary solution. I have C1 matching with this C1. This C4 e to the negative 3x matches with this C2 e to the negative 3x. Don't worry about the fact that the subscripts and the C's are different. That's not important. It's the fact that it's a constant times the same thing, e to the negative 3x there. So these two terms right here come from YC, which means that these two terms in the middle here correspond to the particular solution for this equation because they are unaccounted for in that complementary solution. So what this annihilator approach has done is it's churned out this equation, and when we discard the terms that duplicate what we see in the complementary solution, what's left is the form of our particular solution, meaning we don't have to guess that form anymore. It pops out as a part of this process. So my particular solution, I'm going to lose the C2 and C3 and start calling those, let's say, A x squared plus bx. I have an x squared term and an x term showing up in there. Okay? And then, let's see. I need to proceed as I would have in the previous section. From here, it's undetermined coefficients. It's the same approach that we've been using. So I find yp prime, that's 2ax plus b, and yp double prime, which would just be 2a. Use this in the original DE up here like we were doing in 4.4. So my y double prime looks like 2a plus 3y prime, which here looks like 2ax plus b, and that is set equal to 4x minus 5. Regroup things so that we can solve for those coefficients. I'll get 6ax right here, and then I'm going to have a 3b and a 2a. That makes up my constant term, so 2a plus 3b equals 4x minus 5. And then we've done this process plenty of times by now. In the previous section, we just equate coefficients and solve for a and b. So it's easy enough here to see that a is going to equal, excuse me, 2/3, and b is going to equal negative 19/9. Again, I'm bypassing the algebra for solving these, but it should be pretty straightforward to get that. So now we have our complementary solution. We have the coefficients that we needed for our particular solution. All that's left is to put it all together. So y is equal to c1 plus c2 e to the negative 3x, there's my complementary solution, plus ax squared, which now looks like 2/3 x squared, plus bx, which is minus 19/9 x. There it is. Okay, so notice this approach does not take the work out of solving for those coefficients. If it did, then we wouldn't call this undetermined coefficients anymore. It'd go by some other name. What it changes for us is the beginning of this process, namely the way that we find the form for yp. And again, in our superposition approach, we make an educated guess as to what yp looks like. In the annihilator approach, the form presents itself in this step. Okay, so let's do 2 more examples. That should be enough. This time, we want to solve this second order DE, and we still start the same way as before. We need the auxiliary equation for what we're already given. So that's going to be m squared plus 6m plus 8 equals 0. Let's factor that. That's going to be m plus 2 times m plus 4 equals 0, giving me m equals negative 2 and negative 4. Both of those have multiplicity 1, which means my complementary solution is equal to c1 e to the negative 2x plus c2 e to the negative 4x. Okay? What do I need to do now? Well, the next thing I need to do is find an annihilator for this function right here. Now this one is a linear combination of an exponential function with a polynomial, a linear polynomial. Okay, and what we had done in the previous videos, we show that when we're trying to annihilate a linear combination like this of two different types of functions, what we do is we find an annihilator for each term and then form the composition of those two. So for example, this linear term is going to have d squared as an annihilator. Okay, d squared. This guy right here, this exponential function, e to the negative 2x, because of the negative 2 here, is going to have d plus 2 as its annihilator, okay? And I'm going to apply that to both sides of this equation right here. Now, I already know that because I've chosen this annihilator as it is, this right-hand side is going to become 0. So I'm going to end up with a 0 there. This left-hand side, we saw in the previous example, it was helpful to not actually use y double prime plus 6y prime plus 8y, but instead to write this in operator notation. Notice in operator notation, that's going to look like d squared plus 6d plus 8y. Okay, so this guy right here is just the left-hand side of that dE, but written in operator notation. It's exactly the same thing as this, just presented in a different notation. Okay, that will equal 0. All right. Now I know already what the auxiliary equation for the original dE looked like. It was this, m squared plus 6m plus 8. And notice now that I need a new auxiliary equation for this new equation, the first part of that, the m squared plus 6m plus 8, is already going to show up right here. Right, because we're kind of reusing that. But now I'm picking up two additional factors. So let's keep that in mind. What's the auxiliary equation for this going to look like? Well, it's going to look like m squared from my d squared, d plus 2, and then if I use the factored form of this, or sorry, m plus 2, that's going to become m plus 2. If I use the factored form of this that I found here, here's another factor of m plus 2 that's going to show up. So really, it becomes m plus 2 squared. And then I have m plus 4. That equals 0, okay? You have to be careful with this because it is tempting to not do this thing in operator notation. It's tempting when you're not thinking about where the problem is going to kind of expand all of this out, but then you're going to have to refactor everything anyway. So leave it in this form and then continue factoring down if possible. This gives me the following solutions. M is equal to 0, negative 2, and negative 4. But both of these guys right here, 0 and negative 2, in this equation now have multiplicity 2. So I have to remember to use reduction of order when I'm coming up with their solutions. Okay, so that means that the solution to this homogeneous dE right here is y equals, let's see, so for 0, I'm going to get c1 plus c2x. For negative 2, and both of these terms show up because of the multiplicity here. For negative 2, I'm going to get plus c3 e to the negative 2x plus c4 c4x e to the negative 2x. And then that negative 4 right there is going to give me a plus c5 e to the negative 4x. Okay? What we want to do now is comb through this and identify which terms coincide with the terms of my complementary solution. And I can see I'm going to have an e to the negative 2x term and an e to the negative 4x term. That corresponds to these guys. Okay? Together, those are what my complementary solution are made up of. That means the remaining terms are going to make up the particular solution. So we have yp equals, let's change the c's into, capital A's and B's and C's like we do for undetermined coefficients. A plus bx plus cx e to the negative 2x. That's my particular solution. Okay? You're going to see here, it's a second order equation, so I'm going to have to do up to the second derivative of this guy. And we're going to be using a product rule here to keep things moving along at a good pace. I'm just going to write down what that comes out to after simplifying. So differentiate this, we're going to get b plus ce to the negative 2x minus 2cxe to the negative 2x. My second derivative